In section 3.3, we're going to look at systems of inequalities. This is going to be similar to what we did yesterday, but instead of linear equations, now we're throwing inequalities into it. To see solutions of a system of inequalities, it's by far going to be easiest to look at this by graphing. So if I'm given two inequalities here, I have 2x minus y is greater than or equal to negative 3, and y is greater than or equal to negative 1/2 x plus 1. When I'm graphing, as we know by now, the easiest way to graph is if we're in slope-intercept form. I see that my bottom equation is good to go, so I'll start by graphing that. My y-intercept is at 1, and I'm going down 1 over 2. Solid line because it's greater than or equal to. And finally, I'm shading above, so I'm just going to go ahead and do that. Now I can focus on that other equation. 2x minus y is greater than or equal to negative 3. First things first is I need to get that into slope-intercept form. So I'll bring this down here. And I want to move everything over so the y is by itself, so I'll subtract the 2x. And now to get rid of that negative y, again you could divide or multiply by negative 1. I always like to multiply. And I'm left with y is less than or equal to 3 plus 2x. And remember here, since I'm multiplying by a negative number, I need to flip that inequality, which is why that greater than or equal to turned into a less than or equal to. From here, now I have the y-intercept at 3, and I'm going up 1 over 2. And I want to shade below that because it's less than or equal to. So then I shade below there. From here, now as a graph, I can visually see everything that's an overlapping region or what would be considered a solution. That overlapping region, I'll shade in a different color of yellow to kind of highlight that. And any coordinate in there is going to make both of those equations true or kind of have it be a true solution. So just to see that, I'm going to pick a test point. I'll pick 8, 0. Again, you can pick anything in that yellow region, or even on the line because we're including the line since they're solid. I'm going to plug them into both equations. 16 is greater than or equal to negative 3, so that works out. And 0 is greater than or equal to negative 3, so that also checks out. Any other coordinate, again, that I pick in that yellow region, when I plug them into my original equations, will hold them true. Another thing that I like to focus on is seeing a real-world application here, especially working with inequalities. You'll see that these are going to definitely work in terms of if you have like a limiting factor or something. I think that these are really important to see in a real world sense, or how to set up a system of inequalities just by reading and focusing on the language that's being used. So in this hypothetical scenario, you're purchasing an ice cream sundae at Fiona's. For a regular sundae, sauces cost $2 each, and all other basic toppings, so like sprinkles, crushed nuts, Oreos, would cost $1 each. You know that you want at least 4 toppings, because if you get any less than that, it's pretty boring, but you only have $8 to spend. You want to figure out, judging by that, how many of each type of topping can you put on your sundae. So if I set up a system of inequalities, I could see all the different possible scenarios that I could kind of make for this sundae that fit within my budget. And similar to what you did yesterday, I need to make 2 equations, because I have 2 variables, of cost and quantity. So for the cost, again, I'm going to look at anything that's talking about money in that problem. So I see that sauces cost $2, basic toppings cost $1. I'm going to say that sauces, I'm going to call X, basic toppings, I'm going to call Y. 2 times however many sauces plus 1 times however many toppings. I need to figure out my budget. I only have $8 to spend, so focusing on the language, I can spend up to or including $8. So I'm going to do less than or equal to 8. So my cost equation states 2x plus y is less than or equal to 8. Again, since I have 2 variables, I need to make a second equation. The other thing that I'm talking about in terms of quantity is that I want at least 4 toppings. So for this one, I know that however many sauces, x, plus however many toppings, y, should be greater than or equal to 4. When I see that at least 4, that's the equivalent of saying greater than or equal to. Now I have 2 equations, I can easily get them into slope-intercept form, I could graph, and I could see all my different scenarios. Again, to get slope-intercept, I just get that y by itself. And now I'm good to go to graph. My first equation, I start at 8 and I go down 2 over 1, and I'm going to shade less than. My second equation, I start at 4 as my y-intercept, go down 1 over 1, and I shade above. Since I'm dealing with a real-world equation, anything in the second, third, or fourth quadrant, basically anything dealing with a negative number, isn't necessarily going to make logical sense because I can't have a negative topping. So I'm really just going to look at that overlapping region in the first quadrant, so right here. So now any coordinate that I see in there could work for a combination of sauces and toppings that fit within my budget. So to see a test point, let's try 1, 4. So that means I get 1 sauce, 4 basic toppings. Just looking logically, 1 sauce, 4 toppings, that would be 5 total toppings. Finally, let's test to see if it fits within my budget. 1 sauce times $2 plus 4 other toppings would be $6. That fits within my budget. Let's test another one. Let's do 3, 2. 3 sauces times $2 plus 2 other basic toppings would be $8, which, again, if it's my budget, I could spend exactly $8, so that would work as well. Again, any coordinate within that green region would work out as something fitting within my budget there. Finally, last thing that I want to go over is just showing you one example of when you have a linear inequality and an absolute value inequality. There's nothing really new here, but I think sometimes just seeing a combination, I think it'd be helpful to see one example. Here I have y is less than or equal to 3, and y is greater than or equal to the absolute value of x minus 1. To start, you'll see a lot of these when we work with these in class. If I have y is less than or equal to just a number, constant number, remember that that's just a horizontal line. So my y-intercept is at 3. I'm going to make a horizontal line. I'm going to make it solid because it's less than or equal to. And it's less than, so I'm going to shade below it. So that's it for my first line. Next, for y is greater than or equal to the absolute value of x minus 1, similar to in chapter 2, I want to focus on the vertex of my a-valued graph. This equation here shows me that my vertex is at 1, 0, so I'll plot that. And my a-value, since I don't see anything there, means it's 1. So I'm going to count up 1 over 1. Again, should be a solid line, so I'll make my v there. It's greater than or equal to, so I want to shade above that vertex. So I shade there, and I can see that my overlapping region is that triangle in the middle there. Just to ensure that I did everything correctly, I'm going to do a test point at 1, 1, plug everything in, and I see that both things check out, and I'm good to go.